In this particular lecture, we're going to have a look at steering algorithms as one of the more sophisticated forms whereby we can give our AI-controlled entities the ability to move around or about a particular level or environment. We'll consider quite a few different forms of steering algorithms. Their main strength, however, resides in the fact that they lend themselves to being combined together, that you can define one form and another form and combine both of their outputs, which will be in terms of accelerations, add them together to get a net output. And by combining them in different ways, you actually can provide quite sophisticated forms of movement overall. So steering algorithms, they sit alongside the kinematic algorithms. With kinematic algorithms, we had an instantaneous change of velocity. Here we will be outputting an acceleration, which will be used then to drive the change in velocity, to drive the change in position. And where we want to have games where the objects move smoothly and continuously, then steering algorithms are particularly important. As to the forms of steering behaviour that we'll look at, you can see a list of them here in terms of seek, flee, arrive, wander, and so on. So there's going to be quite a wide range of different ones, and as just mentioned, they can be combined together to produce more complicated, rich forms of movement. More generally, steering algorithms are all about matching a particular target property. So I could try to match a position, so I'm always trying to move in a certain position. I could try to match a velocity and try to move at the same speed. I could try to match an orientation. So steering algorithms are sort of defined on a matching basis. It's also true that for each of the algorithms, in a lot of cases, there's an opposite one. So where seek, you have flee being the opposite version of, and that'll be true for quite a few of these different forms of behaviour. We'll start off first of all having a look at seek and flee. So we compared those in the last talk when we looked at kinematic algorithms. So we'll have a look at how they're created in terms of a steering perspective, and you'll probably see there's very little difference between them. So for seek, we're going to try to match the source position to a target location. We're basically trying to go to a specific target location. We'll determine the direction to the target, and we'll output a maximum acceleration at as fast as we can, accelerating towards that. Because we're outputting an acceleration, that acceleration will update the velocity, and in turn the velocity will update the position. So if we're moving with initial velocity in a different direction, it takes us away from our target, outputting an acceleration will sort of smoothly bend us around towards where it is we want to go to. The algorithm you can see here, and if you sort of look at this, you've got a vector, your source, a vector for your target. These are sort of two positions. Got a maximum acceleration with which you can accelerate at. We're working out the acceleration vector which we're going to return, and there we're doing target minus source, so we're working out a vector from where we're at to where we want to go to. We're normalizing it, so we're keeping the same direction but reducing it down to unit size of length 1, and we're multiplying that by the maximum acceleration in that particular direction. That gives us overall acceleration vector, and we're returning that. And if you look at this comparing against the kinematic seek, it's more or less identical. The only difference is, as opposed to velocities with kinematic algorithms, here we have accelerations. And is that in direction because acceleration updates velocity, updates position, which gives you the smooth movement. The side at the bottom, it mentions that seek accelerates as fast as it can towards the target. It can be useful. In some cases, however, we'll want to slow down when we actually approach the target and not crash into it. So we'll get that through when we have a look at arrive as an extension to seek. Where seek, and the reason seek does give you a smooth output, even though it's functionally the same, is in terms of how we update the position. So as a reminder from last one, we're going to be outputting here an acceleration. It's generally it'll be units per second or per unit time. We'll be calling this frequently so we can get away with the sort of simple Newton-Euler equations. So there we're updating our acceleration with the amount of time that's elapsed for this update to give us a new velocity. This is a positional velocity. We can also have an angular velocity, the rate at which we are rotating or turning our orientation. An angular acceleration is how quickly we're speeding up or slowing down our rotation. So if we define an angular acceleration, again we can use that to update our rotational velocity. For objects, we probably want to, in the same way we're saying we have a maximum accelerative force, we also give them a maximum velocity. So if you wanted to, you could check to see, well, is the speed I'm moving at, which is the length of our velocity vector, if it's greater than some defined maximum, then we normalize it back to unit length and multiply it up by the speed. And you could do the same for the rotation here too. Ultimately, we want to update the position and the orientation, and we do that using the velocity and the rotation, again scaling it by the amount of time that has elapsed. Important to note here that the seek simply outputs a velocity. It changes the position, it doesn't change the orientation. So if we want an entity to move towards another one, but also to change its orientation, for example, to point in the direction it's traveling, we're going to have to combine this seeking behavior with another one of the steering behaviors, which we'll look at later on. Flee is the opposite of seek. And all we do there is we output an acceleration in the opposite direction. Same magnitude, and that will accelerate away from the target as fast as possible. Next up, we're going to have a look at arrive. So as you remember, arrive will take us to a point, will slow us down when it approaches the point, and will then stop whenever we get sufficiently close to the point. In terms of why we need it, if we didn't have arrive and we were simply just using seek, which is maximum speed all of the time, it's likely to be that seek would continue to circle around the target location. Arrive, however, will bring us in, will slow us down, and will then stop when it gets there. As with the kinematic version, we're going to use a couple of different measurements. One's an arrival radius, that when we get within that, we're going to be content that we've reached the target and we'll stop. And the second one's going to be a larger radius, which we'll use as an indicator as to when we should start slowing down. Outside of that slow radius, we'll go there full speed. But as soon as we get within it, we'll slow down and we'll stop whenever we've hit our arrive radius. You can, and there is a defined opposite to arrive called leave. Generally, it isn't used much in games. You quite often you don't want to slowly accelerate away from a particular target position, and the emphasis there being on slowly accelerate. Even if you try to sort of quickly accelerate away, your velocity will start from a low value and then increase as you go up. So flee is generally what you use if you want to have the opposite of arrive. Here's the arrive algorithm. It's similar complexity to the previous one. There's a little bit extra to this. So quite a few parameters we're passing in. We've got our source vector where we're at, our target vector where we want to get to. Our current velocity, we need to know how fast we're moving. We've got maximum acceleration or maximum speed, and then our arrival radius and our slow radius values. Similar to the previous one, we've got a slowing factor. This is an arbitrary variable. We could also pass it in as a property if we wanted the caller to have some control over this. This controls how strongly we decelerate, that whenever we get within the slow radius, are we trying to slow down quickly, or are we sort of waiting until we're much closer into the object before trying to slow down. We also define our output acceleration, and initially we're going to get a value of 0. Then we're calculating a few useful things. So we're getting our direction vector from the target to the source, and taking the length of that direction vector gives us the distance that we are away from our target location. Now, if the distance that we're away is less than the arrive radius, in other words, we're sufficiently close that we're happy, we'll simply return our acceleration, which has been initialized to 0, so we're not doing much. Other than that, we want to determine a target velocity, asking, well, how fast do we want to be travelling towards our target? Having defined the target velocity, we then need to work out, right, what acceleration should we output so that we arrive at and move towards our target velocity. So that's an additional step to put into it. For determining the target velocity, it's going to be very similar to the kinematic one. We've got a target speed. If the distance is greater than the slow radius, so in other words, we're quite far away, we don't want to slow down yet, our target speed is just maximum full speed ahead. If we're within the slow radius, then we pick a target speed that is sort of less, it'll sort of scale down. And as the distance decreases, then our target speed will decrease itself. And then finally, we're producing from that our target velocity. So target velocity is a combination of a speed and a direction. So we go to our direction vector, which separates the source from the target. We normalize it, so we just get direction, nothing else, and we scale that up based on the target speed. That gives us our speed. That's the speed we want to go at. We output an acceleration, and that acceleration will help us hit our target speed. So once we've done that, we then need to think, right, okay, well, what is our desired acceleration? It's simply determined by target velocity minus current velocity. That'll give us the difference that we have from our current speed to the speed that we want to do. That's a good acceleration to output. If you want, you can slow the thing down by the scaling factor, depending on the strength of acceleration you want to apply. And we do a final check here, because it's acceleration they actually do output, that we're not trying to accelerate more than we can in terms of the magnitude of that acceleration. And if need be, we'll normalize it, we'll keep the right direction, but we'll scale it up to the maximum acceleration that we're prepared to output. Past arrive, next thing we want to look at is wander, which is an interesting form of movement. We would use wander if we want to have game entities, unsurprisingly, wander about their world, to sort of walk in a semi-random way. And you might think, okay, let's just use the random function. It's walking in a direction and every so often change. You could do that, but there's a risk it's going to appear to be suddenly abrupt or not particularly realistic forms of movement. So there are some things we can do to help give a more believable or configurable form of wandering. How we can do it is quite interesting. So if I were to imagine myself wandering around, and in order to wander, I'm going to be pointing, I have a certain orientation, facing in a certain direction. I'm going to imagine that there is a circle projected out in front of me. Now that circle will be of a certain size and a certain distance away from me, and these can be properties that I control. On that particular circle, I'm going to have a target, and the target is going to be constrained to the circumference of the circle. And wherever that target is, that's where I'm going to head towards. So you can see it here. I've got my triangle at the bottom. I've got my wander target, which is a point in the circle I'm projecting ahead of myself, and that will determine the direction that I'm seeking towards. What gives the wander behavior is that each second, or each update, I'm going to move the target around the circumference of the circle. I'm restricting it to beyond that circumference, but each update I'll move it a little bit one way or the other. So it's the target's shifting about that particular surface. And that means that each time I'm moving towards a different location. And by varying the size of the circle, the distance from the actual character that's moving, how fast the target moves around the circle, you can get all the way from a sort of a wander behavior that seems to be in sort of an aimless wander around, more or less in a straight line about the environment, all the way to very quite sophisticated sort of pirouetting behavior, almost a dancing-like behavior, where your sort of wandering character dances or moves around in circles and loops. So it's quite a simple idea, but it's quite a capable one in terms of how flexible it is. How to implement it? It's reasonably straightforward to implement it. We've got a whole bunch of parameters we're passing in for where we're at. Our source orientation, our max acceleration, the wander offset, the wander radius, the wander rate itself, and the wander orientation. You can see all of those values in the diagram on the right. We've got our source where we're at. We're projecting out based on our orientation a certain distance, the wander offset, which gives us the center of the circle. The actual circumference or outer ring of the circles will be the wander radius. That will define that overall circle. And the target is going to have a certain orientation relative to 0 around that particular circle. And each update, we will move it by a wander rate around the circumference. So the first thing we do is that when we're calling this, okay, we've got to give it a new wander target. So it's simply, we update the orientation, add it on the rate, this is how fast we're prepared to move, multiply it by some random value. So here's a random binomial. But binomial is like a bell-curved one, so most of the values will be around the center of a few outliers, though any sort of random function works here where we can change our wander rate by some random amount. Binomial function just happens to give you sort of slightly more smoother movements. Having updated the wander orientation, we then work out, well, what is our target orientation? Where do we want to be pointing towards? And that is the same as our source orientation, the way we're currently orientated, adding on the wander orientation, the angle towards the seeking point. So that gives an indication of what a sort of our net orientation actually is. We want to work out a point then that we can seek towards. And to do that, we're building it up in these two lines. So we start off in our source, this is whereabouts we're at. We add on to the source the wander offset multiplied by a vector. And it's going to be a directional vector that corresponds to the source orientation. So our source orientation is if we express it as a directional vector, is the vector that will take us towards the center of the circle. And it'll be a distance of wander offset will go along that. So that one first line will bring us from where we're at to the center of the circle. The second line where we're adding on to, so wander plus is equal to the wander radius, which is how far we have to go out to hit to the circumference of the circles, times, again expressed as a vector, because we're updating vectors here, the target orientation expressed as a directional vector. And adding that line on means we go from the source to the center, we go from the center of the circle out to the particular point. And it's going to give us a vector, an x and a y coordinate, a position of that particular target in our game world. How you actually do that, you can see here, if you pass in an angle, you be using cosine and sine, you can return a directional vector, a vector which corresponds to that particular angular expression. Now, given that particular target, all we're doing then is we're going to our seek steering behavior, and we are seeking towards that particular target. This is known as a delegate behavior, that we do a bit of work and then we delegate, we pass off the rest to the seek behavior. It does the rest of the work. So it can be hard to visualize just how capable this is. It's good to actually implement it and to play about with the values and then to get a feel for the type of orientation and wandering you can get out of it. After this we have pursuit, and the opposite of pursuit, known as evade. Now, seek works by heading directly towards the target. Fair enough. It's not an optimal form of trying to get to the target, however, and if you were thinking about chasing after somebody, you wouldn't run to where they're currently at. You would ask yourself, okay, what direction are they running? I'm going to try to have a guess as to where they're going to be in a few seconds' time. That's where I'll run to. So it's a predictive one. So for this one here, we want to predict for our target, which is moving, where is it going to be in the future. You may think, oh, it's a very difficult thing to do. And it can be a very difficult thing that's trying to avoid being caught. The one thing that works in our favour here is that we are doing this very frequently, 20, 30, 50 times a second. So we're making lots of guesses as to where it's going to be, but then we're very quickly updating that guess. And because of that, it means we can use quite a simple predictive model of where it's going to be. And because we're updating it frequently, correcting it frequently, it's actually quite an effective way of doing it. So a simple but yet effective way is to simply assume it's going to move in a straight line based on its current velocity. So I'll take where the target is, I'll add on its velocity a certain distance in the future, and that's the location I will seek towards. By way of a fragment of code, it's not horrendously complicated, it's reasonably straightforward. We take in our source vector, where we're at, our target vector, where we want to get to, or what we're chasing after rather. The velocity then we'll need to know what speed we're moving at, and the target velocity we also need to do what speed's the other thing moving at. And we want to output from this an acceleration that will head towards or pursue the target. We've got a variable here now. You could pass this as a parameter if you wanted to, or you could just hard code it within the method. This is the distance. How much into the future are we prepared to predict? So are we prepared to predict the location of the target in half a second, in 1 second, in 10 seconds, in 2 hours time? There'll be an upper limit beyond which we won't want to do our prediction. We do a little bit of work here to work out, okay, what is the direction from the target, from the source that we're currently at. We work out the distance that we are away, and importantly, we work out the speed with which we are moving. We then do a little test here. We work out, based on the distance we are apart and the speed that we have, roughly how far away are we? Do we think we're reasonably close? Do we think we've got a long distance to go? And we cap this based on the max prediction. So based on our current distance and our speed, if we're 5 seconds away from the target, but we're only willing to predict 2 seconds ahead, then it's only 2 seconds we'll predict. If we're half a second away based on our current velocity, then we'll use that. We'll predict where the target's going to be in half a second as opposed to 2 seconds. So it's a way of sort of fine-tuning in it. The prediction is as straightforward as it gets. You know where the target's at, you know the velocity the target has, so you update the position to include the velocity-induced change in position at that point in the future. And then finally, again, it's a delegate behavior, you seek towards that future point. So very straightforward, but actually gives you a more effective form of seeking or pursuit. Evade is very simply defined. It's the opposite. You evade, you run away, you flee from where you think the target's going to be in the future. The only difference is you do all exactly the same stuff here, but you don't seek, you flee. So nicely straightforward. Interpose is related to pursuit. In this case, we're trying to get in between two objects. So we're going to have a sort of two targets. We're going to, this could be a player and a ball, and the ball's moving, the player's moving. We'll predict where the player's going to be in the future. We'll predict where the ball's going to be in the future. That gives us 2 points we're doing our prediction for. And we'll take the midpoint between those 2 points. So we're getting in the middle, and we'll then seek towards that particular middle point. Now that's predictive to interpose. You can also do the non-predictive version. You just want to ask, well, where's my 2 points? I'll head to the middle. Quite good in sports games where you do want to intercept and get in between an object and or a couple of target objects. Next up, we're going to have a look at alignment. All of the previous ones were outputting an acceleration to give you a velocity, gives you an updated position. Align's the first one we're going to have a look at that outputs an angular acceleration. So it changes the rotational speed, which changes the orientation. So align tries to match the orientation of the source of the target. So if you give me a target, I'll try to point in the same direction that the target's pointing. There's no linear movement here, we're just rotating the object. The align algorithm we're going to have a look at is going to be very, very similar to arrive. So arrive, where you head towards something, you slow down and you stop, is exactly the same behavior you want to use for align. The one complicating factor here is that in terms of the x and the y, it was sort of infinite in the extent. In terms of an angle, it actually repeats. So we go from 0 to 360. 361 is the same angle as 1. So it is a cyclic one. because of that, we'll want to standardize our angles to put them in the, here we're standardizing to the minus 180 to 180 range. And it just gives us a way of working out actually how far apart are the two angles when we put them into the same standardized range. So that will be the one complicating factor. Similar to arrive, we'll have a couple of triggers, one for when we're sufficiently close if we don't want to rotate any more, and the other one which well, if we're outside we'll be rotating, turning as fast as we can, but when we get within it we'll slow down the speed of our rotation. So here we have the code. It's going to be very, very similar to the arrive one. We're not passing in vectors here for the position, we're passing in our source orientation and our target orientation. We've got a maximum angular acceleration, a max rotation, arrive angle, slow angle. Again, we have a slowing factor. It can be passed in as a parameter if you want it to. And we have our angular acceleration. How fast do we want to change, what strength do we want to change the rotation? We work out, well, how far off our target are we? And here we're standardizing it within this particular range. The target minus source is the difference. Gives it a standardized one. And we check to see, now, if you think about it, we might be 5 degrees out. Now, it could be 5 degrees to the left, it could be 5 degrees to the right. So you have a negative and positive. The rotation size, you can see here we're using the absolute value of the rotation. So at this point in the algorithm, we just want to work out how far away are we, and we're not interested if we're rotating to the left or to the right. It's just how much rotation do we need to eke out. We'll introduce the sign in a little bit. If the amount of rotation we have to do is less than the arrival angle, in other words, we're sufficiently close that we're happy, we simply return our angular acceleration of 0. We don't do anything. Other than that, we want to determine, well, how fast do we want to rotate? And then we want to return, well, what angular acceleration will give us this rotation? So it's quite similar to arrive. For the target rotational speed, very, very similar again. We work out, okay, are we greater than the slow angle? If so, we're rotating as fast as we can. Other than that, we're going to pick a rotation sort of scaled on how far out that we actually are. And the slow radius here can be used to control how drastic that reduction is. The target position then, signum is built into most MAS libraries. If you've got a positive value, it returns 1. If you've got a negative value, it returns -1. So by multiplying it with the signum of the rotation, which if you look over on the left-hand side was the thing that we calculated, which did take into account if it was a negative or positive angle. Here, our target rotation gets to be updated to include the right sign. So we're moving in the right direction at the right speed. Determine the angular acceleration, very straightforward again. We know our current target rotation, we know our one we want to go to, work out the difference between the two. If we want, we can slow it down based on the slowing factor. Check to see, are we trying to have an angular acceleration bigger than what we can support? And if so, then scale it down. So fundamentally, same as arrive, but here, not applied to vectors, applied to scalar rotation. Face is a bit of an extension to a line. If you're calling face, you say, okay, well, that's where I'm currently at. I want you to look towards some other object. So there we're giving an object in, and we will want to turn and look at that particular position. So a simple thing to do, you basically work out target minus source, gives you the direction vector to that. Normalizing that, you get a unit vector, you can work out then the orientation, and you pass that into the align method. So face is just simply one way of calling alignment. Look where you're going is another one, and it's a simple form of movement. Again, it's based on aligned delegate behavior. So we're going to work out something, then we're going to pass that on to align. For look where you're going, as the name suggests, whatever velocity you have, you change your orientation so it is in the direction of the velocity as well. So we're doing this one here, we make sure we actually do have a velocity, else we're not going to change the orientation. If we do, we're using our arctan 2, which is the one that will take in our current velocities and give us an angle, and we're then passing that angle into our align method. Separate then, a rather sad looking image, is the next type of steering behaviour we want to have a look at. The way separate works is it tries to, if you assume here you have a bunch of objects, this works in multiple objects, and you don't want those objects to get too crowded. So as one object approaches into, if you like, the comfort zone of another object, the object tries to move out of the way, so they try to maintain a separation. For the diagram here, we've got our triangle in the centre. We've got a number of points around it, and we're trying to move away from all of those. And depending upon how close that we are, so the closer we are to the target, the greater the force will have pushing us away. The nice thing about accelerations is that if you have multiple forces, you can add them all up. You can get a net acceleration which sort of balances all of those different accelerative values. Piece of pseudocode here, what we're passing in ourselves as the source. We're assuming we have an array of targets. These are points that we want to avoid. We've got a separate threshold, so this will determine how close you can get before the object wants to run away. We've got a separate decay, and this will determine, okay, as soon as you go over my threshold, am I trying to get away immediately with a great strength, or do I wait until you're in closer to me and then I try to move away? So it really determines the strength and the immediacy of the separation. And similar to other ones, we have a maximum acceleration. Well, how fast can we try to get away from something? So we've got our output acceleration. This is our net acceleration, which we'll build up as we go through. We're going through each of the objects that we have in our array of targets. We're working out a directional vector from the source, where I am, to where I want to get to. So this is the particular target, this is what the separation is, and I'm working out that particular distance. Now if the distance is less than the separation threshold, that means that something sufficiently close to the object's not comfortable, it wants to move away. We want to trigger some action, we want to work out, well, how fast should I try to move away? We've got a few components here. It's a minimum, so we're going to take the minimum value, and we've got separate decay times distance is one of the terms, and max acceleration is the other term. So we're going to calculate a value here. That value might be larger than max acceleration. If it is, the minimum function will ensure that we don't return something bigger than max acceleration, but it might be less. It's a distance squared metric, and again you could just do separation decay times distance if you wanted to, which would be a linear decay one here. This one by distance means that the closer you get in, the bigger the response to try to get away, but it's always capped by our maximum acceleration. Having calculated the strength, then we work out the direction that we have from our source to where we want to go, and we multiply that by the strength of us trying to get away, and we add that onto our acceleration vector. Now it is adding it on, so this is part of the for loop, and we'll go around and do this for all of the objects, and we'll keep accumulating the acceleration. Finally, at the end, we check to see, okay, we've potentially added a lot of things onto the acceleration. Let's just make sure we haven't got a net acceleration which actually breaks our maximum value. So we do a final check here to make sure that we have a valid acceleration, normalizing it if we need to do so, and then we return that. So that's it. We've got a couple of key takeaways. There's lots of different forms of steering behaviour that can be defined. You've seen quite a few of them here. They're designed to be combined together, that I could take a pursuit behaviour towards, say, chasing after the player. I could add in a separate behaviour to try to stay apart from another bunch of objects. I could add in sort of a look as you're moving, so I always face towards the direction. And because we're outputting accelerations and angular accelerations, you just add them together. So that's the strength of the steering behaviours is their ability to combine them in different ways to give potentially quite sophisticated forms of behaviour overall.